What if the ingredients for life didn't begin on Earth at all? Picture this: countless stars, galaxies stretching beyond sight, and drifting through the cosmic void, tiny molecules that would one day become the building blocks of everything alive. The universe is unimaginably old, and yet we're still uncovering clues about how those first organic molecules, the ones that sparked life itself, could have formed in the vast emptiness of space. It's one of the greatest mysteries science has ever tackled. How did lifeless atoms come together to create the complex chemistry that eventually led to you, me, and every living thing we know? For decades, researchers have chased answers, piecing together theories that sound like something from science fiction. Some say these molecules could have been forged in the hearts of dying stars, then scattered across the cosmos by violent supernova. Others argue they might have formed right here on Earth, deep in the ocean's hydrothermal vents, or even within the fiery chaos of lightning strikes. And then there are the wilder ideas, like the possibility that these essential ingredients hitched a ride on comets, raining down on our planet from the icy depths of space. Every theory is a piece of the puzzle, and each one pushes us closer to understanding where life truly began. That's exactly what we're diving into today. 30 breathtaking theories about how the universe's first organic molecules came to exist. Some are backed by solid evidence, others are still just tantalizing possibilities, but all of them open doors to the incredible story of how life found a way. Whether you're a science enthusiast or just someone who loves a good cosmic mystery, this journey will take you from the birth of stars to the tiniest chemical reactions that might have changed everything. So let's peel back the layers of time and space and explore the incredible ideas that could finally answer one of humanity's oldest questions: where did life really come from? One of the oldest and most enduring theories about life's chemical origins takes us back to Earth's violent infancy. Picture a planet still cooling from its fiery birth, covered in erupting volcanoes, churning oceans, and skies crackling with endless lightning. In the 1920s, two scientists, Alexander Oparin and J.B.S. Haldane, independently proposed that this chaotic environment might have been the perfect laboratory for brewing life's first ingredients. Their idea, later nicknamed the primordial soup hypothesis, suggested that Earth's early atmosphere, rich in methane, ammonia, and water vapor, could have reacted under lightning strikes or ultraviolet radiation to form simple organic compounds. Decades later, in 1953, a pair of young researchers named Stanley Miller and Miller-Urey brought this theory to life in one of the most famous experiments in science. They sealed those same gases in glass flasks, added sparks to mimic lightning, and watched as something astonishing happened. Within days, the mixture turned murky, a broth of amino acids, the building blocks of proteins, had formed. Suddenly, Oparin and Haldane's idea wasn't just speculation, it had experimental proof. But science never stands still. While the Miller-Urey experiment was groundbreaking, later discoveries cast doubt on whether Earth's early atmosphere was truly as hydrogen-rich as they assumed. Some geochemists argue it might have been dominated by carbon dioxide and nitrogen instead, gases far less likely to spark life's chemistry under those conditions. Others point out that amino acids, while essential, are still a long way from the complexity of actual living cells. It's like having flour and eggs but no recipe to bake a cake. Yet the primordial soup theory refuses to fade away entirely. Recent tweaks to the original experiment, using more accurate atmospheric mixes or adding minerals from deep-sea vents, have shown organic molecules can still form under varied conditions. Maybe lightning wasn't the only chef in the kitchen. Volcanic heat, solar radiation, or even meteorite impacts could have stirred the pot. The beauty of this idea lies in its simplicity. No need for interstellar delivery or cosmic accidents, just Earth, time, and the raw energy of a young planet figuring out how to cook up life from scratch. Deep beneath the ocean's surface, where sunlight never reaches and pressures could crush a submarine like a tin can, lies another possible birthplace for life's earliest molecules. Hydrothermal vents, those otherworldly chimneys spewing superheated, mineral-rich water, might seem like the last place you'd expect delicate organic chemistry to thrive. Yet these extreme environments have everything needed to turn simple elements into the complex building blocks of life. The magic starts with the vents themselves. Cracks in the ocean floor allow seawater to seep down, where it's heated by Earth's molten core before erupting back up, loaded with dissolved metals and sulfur. This creates a natural laboratory, with temperature gradients ranging from scorching hot to icy cold, perfect for driving chemical reactions, but the real game changer. The porous rock structures around the vents, filled with microscopic nooks and crannies that act like tiny test tubes. Minerals like iron and nickel embedded in these rocks can serve as catalysts, helping simple molecules link together into more complex ones without being destroyed by the harsh conditions. Scientists have even recreated these environments in labs, simulating vent chemistry by mixing water, minerals, and gases like carbon dioxide under intense pressure. The results: amino acids, sugars, and even lipids, the very ingredient cells need to form, and it's not just theoretical. In recent years, researchers exploring actual hydrothermal vents have detected organic molecules clinging to the mineral surfaces, as if the vents themselves are quietly assembling life's toolkit. What makes this theory so compelling is how it solves some of the biggest puzzles in the origin of life. The vents provide stability, a sheltered space where fragile molecules can accumulate without being scattered by waves or UV radiation. The energy isn't just a fleeting lightning strike, it's constant, fueled by Earth's own geothermal heat, and the mineral surfaces don't just protect these molecules, they might have helped them organize, almost like a molecular scaffolding guiding them toward greater complexity. It's as if the planet itself was nudging chemistry toward biology. Of course, there are still gaps. While vents excel at creating life's ingredients, getting those ingredients to self-assemble into something resembling a living cell is another challenge altogether. Some critics argue the vents are too chaotic, their conditions too variable for such precise chemistry, but every year, new discoveries add weight to the idea. From underwater volcanoes in the Pacific to icy vents on moons like Europa, the universe seems to be whispering that life might favor the heat, the dark, and the quiet hum of chemistry unfolding in the deep. Now let's take a step, or rather, a leap beyond Earth. What if life's building blocks didn't originate here at all? Imagine organic molecules hitching a ride across the cosmos, tucked inside comets or meteorites, until one day they crashed into our planet and jump-started the entire story of life. This idea, known as Panspermia, turns the universe into a grand delivery system, with Earth as just one lucky recipient in a vast interstellar network. The evidence for this theory comes from some of the most unassuming rocks in existence, meteorites. Take the Murchison meteorite, a space rock that fell in Australia in 1969. When scientists analyzed its composition, they found something astonishing: over 90 different amino acids, including some not commonly found on Earth. Even more intriguing, these molecules showed a slight preference for one mirrored form over another, a trait often linked to biological processes. It's as if the meteorite carried not just the ingredients for life, but a hint of the asymmetry that defines living chemistry. But how could fragile organic compounds survive the violent journey through space? The answer lies in the protective embrace of ice and rock. Comets, those icy wanderers from the outer solar system, are loaded with water, methane, and ammonia, all key ingredients for organic chemistry. As they drift through the cold void, cosmic radiation can trigger reactions on their surfaces, slowly building more complex molecules, and when a comet or asteroid enters a planet's atmosphere, its outer layers might burn away, but the shielded interior could still deliver its precious cargo intact. Even more mind-bending is the discovery of formaldehyde floating in interstellar space. This simple molecule might not sound impressive, but it's a stepping stone to sugars like ribose, a critical component of RNA, the molecule many scientists believe came before DNA in the earliest forms of life. Telescopes have spotted formaldehyde in vast molecular clouds, the same nurseries where stars and planets are born. If these clouds can brew such compounds, then every new planetary system might be seeded with the raw materials for life from the very beginning. Panspermia doesn't just reshuffle where life's chemistry began, it reshapes our entire perspective on life's cosmic potential. If organic molecules are common space travelers, then planets, moons, or even rogue celestial bodies drifting between stars could carry the same primordial spark. Suddenly, the universe feels less empty and more like a network of possibilities, where life might be waiting for the right conditions to take root. Yet the theory isn't without its skeptics. Some argue that even if space delivered the ingredients, Earth still had to do the heavy lifting of assembling them into something alive. Others question whether delicate molecules could truly endure millions of years of radiation and extreme temperatures. But here's the thrilling part: we're still collecting clues. Every new meteorite analysis, every detection of complex molecules in a distant gas cloud, adds another piece to the puzzle. Whether panspermia proves to be life's origin story or just one chapter in a much larger tale, it reminds us that Earth isn't an isolated laboratory. We're part of a dynamic, interconnected cosmos where the lines between chemistry and biology might be written in stardust, floating between the stars, where temperatures hover just above absolute zero and the void seems impossibly empty. An unexpected kind of chemistry might have been quietly crafting life's ingredients. Tiny specks of cosmic dust, each no larger than a grain of sand, could have acted as microscopic laboratories, transforming simple atoms into complex organic molecules under the relentless glow of starlight. NASA telescopes have spotted something remarkable in these vast interstellar clouds: polycyclic aromatic hydrocarbons, or PA. These aren't just random space junk, they're intricate carbon-based structures resembling tiny chicken wire cages, built from rings of atoms linked together. While they might sound obscure, pHs are everywhere, found in meteorites, comets, and even the haze of distant nebulas. What makes them so fascinating is how they form. When ultraviolet light from nearby stars hits these dust grains, the energy can kickstart reactions, coaxing lone carbon and hydrogen atoms to snap together into these intricate ringed molecules. Think of it like a cosmic bakery. The dust grains are the mixing bowls, and UV radiation is the oven. As starlight bombards the grain's surfaces, it provides just enough energy for atoms to shuffle around, bonding in ways that would never happen in the cold depths of space otherwise. Over millions of years, this slow, steady process could build molecules far more complex than anyone once thought possible in such a harsh environment. And here's the twist: pHs aren't just relics of ancient chemistry. Some researchers believe they could be precursors to even larger organic compounds, like the nucleobases that form DNA's alphabet. This isn't just speculation. Lab experiments here on Earth have recreated these conditions, blasting icy dust analogs with UV light and watching as organic molecules emerge. In one study, scientists produced uracil, a key component of RNA, under conditions mimicking interstellar space. It's as if the universe has a hidden recipe, written in starlight and dust, for assembling life's raw materials. Yet cosmic dust chemistry raises its own mysteries. How do these delicate molecules survive the turbulence of space, where radiation and collisions should tear them apart? Some theories suggest the dust grains themselves act as shields, their porous surfaces offering safe havens where molecules can grow undisturbed. Others propose that pHs might clump together, forming protective layers like a molecular armor. What's clear is this: if even a fraction of these cosmic molecules made it to young planets like Earth, they could have delivered a starter kit for life. From the faint glow of distant nebulas to the silent dance of dust around newborn stars, the building blocks of biology might have been woven into the fabric of the universe long before Earth even existed. While we're still piecing together how these processes work, each discovery paints a grander picture, one where life's origins aren't just a planetary story, but a celestial one. Ever wonder if the very ground beneath our feet could have been the architect of life's first molecules? Picture a world before soil, before plants, where the Earth's surface was a patchwork of volcanic rock and bubbling pools. In this primordial landscape, one of the most unassuming materials, clay, might have played a starring role in shaping the chemistry that led to life. Here's why scientists are so intrigued. Clay minerals, with their stacked, sheet-like structures, aren't just passive dirt. Their surfaces are riddled with tiny electrical charges and microscopic gaps, perfect for attracting and holding onto organic molecules like a molecular magnet. But clays don't just collect these molecules, they can organize them. Imagine a messy desk cluttered with papers. Now picture someone coming along and stacking those papers neatly, aligning every corner. That's essentially what clay does with molecules, bringing order to chaos. In the 1980s, a chemist named James Ferris made a breakthrough discovery. He mixed simple nucleotides, the building blocks of RNA, with montmorillonite clay, a common mineral found in volcanic ash. Left alone, these nucleotides might have floated aimlessly in water, rarely linking up. But with clay as a template, something remarkable happened. The nucleotides lined up along the clay's charged surface, snapping together into chains up to 50 units long. It was as if the clay provided a blueprint, guiding random chemicals toward the complexity needed for life. This isn't just lab magic. Clays are abundant in nature, especially around geothermal areas where hot water percolates through rocks, leaching out minerals. These environments would have been common on early Earth, offering countless nooks where chemistry could experiment, and the advantages of clay go beyond just assembly. Its layered structure can shield delicate molecules from destructive UV radiation or sudden temperature shifts, acting like a microscopic incubator. Some researchers even suggest that clays could have helped concentrate rare molecules, turning a dilute primordial soup into a rich broth ripe for reactions. But the story gets even stranger. Certain clays don't just assemble molecules, they can select them. Experiments show that some clay minerals favor specific molecular shapes or orientations, subtly steering chemistry toward the kinds of complexity seen in biological systems. It's almost as if the Earth's geology had a hidden preference for the patterns that life would eventually adopt. Of course, clay alone doesn't solve every mystery. While it excels at organizing small molecules, bridging the gap to self-replicating systems like RNA remains a puzzle. Critics point out that clays might trap molecules too well, preventing them from interacting freely. Others argue that without a constant energy source like the heat from hydrothermal vents, the process might stall, yet the theory holds a compelling elegance. Unlike lightning strikes or comet impacts, clay offers a slow, steady hand, a geological midwife patiently guiding chemistry toward biology. From the bubbling mud pots of Yellowstone to the ancient sediments of Mars, this humble material might be a universal catalyst, quietly scripting life's first chapters in the unlikeliest of places. Every time we walk past a riverbank or a crumbling cliff, we could be brushing against the remnants of Earth's oldest laboratory, deep inside Earth's fiery belly, where molten rock churns and gases hiss through cracks in the planet's crust. Another unlikely player enters the story of life's origin: cyanide. Yes, that infamous poison, but long before it became a symbol of danger, this simple molecule might have been the unsung hero in crafting life's earliest building blocks. Volcanoes don't just spew lava, they release plumes of gas rich in carbon dioxide, nitrogen, and sulfur. When these gases rise into the atmosphere, they're bombarded by ultraviolet light from the sun, a relentless energy source capable of breaking and reforging chemical bonds. In the chaos of these reactions, something extraordinary can happen. Nitrogen and carbon atoms, which would normally ignore each other, get forced together under UV radiation, forming hydrogen cyanide. This compound, though toxic to most modern life, is a versatile chemical workhorse. It can react with water, metals, or other gases to create adenine, a key component of DNA and RNA. Here's where the chemistry gets captivating. In lab experiments simulating volcanic plumes, researchers have recreated these conditions, mixing gases like carbon dioxide and nitrogen under UV lamps. Within hours, the mixture yields not just hydrogen cyanide, but also formaldehyde, another critical precursor for sugars like ribose. It's as if the violent skies of early Earth were a giant, natural reaction flask, brewing life's ingredients in plain sight. But why volcanoes? Unlike lightning strikes or hydrothermal vents, volcanic plumes offer something unique: scale. A single eruption could pump vast quantities of reactive gases into the atmosphere, creating a planet-wide chemical workshop. And because UV light penetrates these plumes so deeply, the reactions wouldn't be confined to the ground, they'd unfold across the entire sky, raining organic molecules back down in a constant, planet-wide drizzle. There's another twist: cyanide isn't just a precursor, it's a catalyst. Under the right conditions, it can drive the formation of amino acids and nucleobases, acting like a molecular matchmaker that brings other compounds together. Some scientists even suggest that cyanide's reactivity could have helped bypass energy barriers, allowing life's chemistry to advance faster than it would in gentler environments. Of course, skeptics raise valid questions. Would these molecules have survived the violent winds and rain of early Earth? Could enough have accumulated to make a difference? Recent models suggest yes, especially if volcanic activity was as relentless as geological evidence implies. And let's not forget, while cyanide is deadly to us, primitive life wouldn't have had our vulnerabilities. For a world without oxygen in its atmosphere, cyanide might have been just another tool in the chemical toolbox. What's striking about this theory is its universality. Volcanoes aren't unique to Earth, they're found on Mars, Venus, even Jupiter's moon Io. If volcanic gases can indeed spawn life's precursors, then the recipe for biology might be written into the very geology of rocky planets. Next time you see a volcanic eruption on the news, consider this: those plumes of ash and gas could be echoes of the process that turned a lifeless planet into a living one. Nikola Tesla, the visionary inventor who harnessed the power of electricity like no one before him, might have stumbled onto a clue about life's origins without even realizing it. While his experiments with high-voltage currents were meant to revolutionize energy transmission, they accidentally revealed something far more profound: how lightning-like sparks in methane-rich environments could forge the very molecules life depends on. In the late 19th century, Tesla was busy perfecting his famous Tesla coil, a device capable of generating massive electrical discharges. During one experiment, he sealed methane gas, a simple compound of carbon and hydrogen, inside glass tubes before subjecting them to controlled bursts of artificial lightning. The results were startling. The sparks didn't just ionize the gas, they transformed it, producing acetylene, a molecule built from two carbon atoms triple bonded together. This wasn't just a laboratory curiosity. Acetylene is a chemical Swiss Army knife. Under the right conditions, it can react to form everything from benzene rings to amino acids, the very scaffolding of organic chemistry. Fast forward to modern experiments, and scientists have confirmed Tesla's observations with even more precision. When methane-dominated atmospheres, like those thought to exist on early Earth, are exposed to electrical discharges, the energy doesn't just break bonds, it rearranges atoms into increasingly complex structures. Formaldehyde, hydrogen cyanide, even sugars begin to emerge from the chaos, as if the spark itself is a sculptor shaping raw elements into biological potential. What makes this process so compelling is its simplicity. Unlike hydrothermal vents or interstellar dust, which require specific geological or cosmic conditions, electric discharge is universal. Lightning crackles through the skies of every stormy planet, from Venus to Saturn. On a young Earth where volcanic outgassing could have saturated the air with methane, every thunderstorm would have been a factory for organic molecules, raining them down into oceans and lakes below. But here's the twist: methane isn't the only gas that plays well with sparks. Add nitrogen and you get cyanide, the same molecule that might have jump-started DNA's precursors in volcanic plumes. Introduce water vapor, and the reactions branch further, weaving oxygen atoms into the mix. It's a chemical domino effect, with each spark setting off cascades of complexity. Critics of this theory point out that Earth's early atmosphere might not have been as methane-rich as once believed, potentially limiting the efficiency of these reactions. Yet recent studies suggest workarounds. Local methane pockets near volcanic activity or comet impacts could have created temporary hotspots for spark-driven chemistry, even in a less reducing global atmosphere. And let's not forget Tesla's experiments didn't just simulate lightning. They revealed how any energetic discharge, from volcanic sparks to asteroid-induced plasma, could achieve similar results. The beauty of this idea lies in its raw, elemental power. No delicate mineral templates or cosmic dust shields, just the brute force of nature's electricity, hammering simple molecules into something greater. Next time you see a lightning storm illuminate the sky, remember, those dazzling bolts might be echoes of the very process that wired life's first circuits. Along coastlines where the tides ebb and flow, another subtle yet powerful force could have helped life's earliest molecules take shape. Imagine shallow pools trapped between rocks, filled with seawater rich in organic compounds. As the sun beats down, water slowly evaporates, leaving behind a concentrated brew of chemicals, like reducing a sauce to intensify its flavor. This simple act of nature, repeated over countless cycles, might have been the missing ingredient that transformed scattered molecules into the foundations of life. Modern analogues like Shark Bay in Australia offer a window into this process. Here, tidal pools teem with microbial life, but it's the chemistry of these pools that's most revealing. Researchers have found that as water evaporates, dissolved organic compounds, amino acids, lipids, even nucleotides, don't just linger, they interact. The increasing concentration forces molecules into closer proximity, making reactions inevitable. It's a bit like cramming people into a crowded room. Sooner or later, conversations start. In the case of tidal pools, those conversations are chemical bonds forming, chains lengthening, and complexity emerging. But concentration isn't the only benefit. Tidal pools experience constant change, flooding with fresh seawater, then drying again. Each cycle brings new ingredients while removing waste products that could inhibit reactions. This dynamic environment acts like a natural purification system, favoring molecules that can withstand the shifting conditions. Over time, the pool becomes a nursery for resilient compounds, selectively amplifying those with the right properties for life's next steps. Laboratory experiments back this up. When scientists simulate tidal pool conditions alternating wet and dry phases with organic-laden water, they observe something remarkable. Not only do molecules like amino acids link into chains, but some even form tiny, cell-like structures called vesicles. These hollow spheres made of fatty acids mimic the membranes of modern cells, suggesting that tidal pools could have been where life first learned to package itself. What makes this theory so elegant is its universality. Tidal pools don't require rare or extreme conditions, just a coastline, sunlight, and time. On early Earth, with vast shallow seas and no ozone layer to block UV radiation, these pools would have been ubiquitous. And the implications stretch beyond our planet. Mars once had oceans, and its ancient shorelines might have hosted similar environments. If tidal pools can concentrate and organize molecules here, why not elsewhere? Yet questions remain. Could delicate molecules survive the harsh UV exposure of an unshielded Earth? Some research suggests that minerals or organic films might have formed protective layers on the pool surfaces, acting as natural sunscreen. Others argue that the sheer volume of tidal pools would have made occasional successes inevitable, even if most attempts failed. The tidal pool hypothesis doesn't just explain how life's ingredients could have gathered, it shows how ordinary natural processes, repeated across millions of years, might have turned randomness into inevitability. Next time you see a tide recede, leaving behind glistening puddles, consider this: those fleeting pockets of water could hold the echoes of a process that turned chemistry into biology, one evaporating drop at a time. Among the countless theories about life's origins, one of the most intriguing takes us to an unexpected place: radioactive beaches. Picture this: stretches of sand along Earth's earliest coastlines, glinting not just with ordinary minerals, but with tiny grains of uranium and thorium. These naturally occurring radioactive elements, often dismissed as hazardous today, might have played a crucial role in jump-starting the chemistry of life. The idea hinges on a process called radiolysis. When radioactive minerals decay, they emit energetic particles, alpha, beta, and gamma radiation, that can rip through surrounding water molecules, breaking them apart into highly reactive fragments. These fragments, including hydrogen peroxide and free radicals, don't just vanish, they act as tiny chemical power tools, driving reactions that would otherwise stall in the gentle warmth of a primordial ocean. In the case of early Earth's beaches, the constant bombardment of radiation could have provided the energy needed to link small organic molecules into long chains, a critical step toward the complexity of life. Evidence for this theory comes from an unlikely time capsule: zircon crystals. These incredibly durable minerals, some older than 4 billion years, trap tiny pockets of the ancient environment inside them like microscopic amber. When scientists analyzed zircons from Australia's Jack Hills, they found hints that the beaches of early Earth were indeed laced with radioactive elements. Even more compelling, lab experiments have shown that radiation from uranium-bearing sands can produce exactly the kind of energized chemistry needed to polymerize amino acids and nucleotides, the building blocks of proteins and genetic material. But why beaches? Unlike deep-sea vents or tidal pools, coastal sands offer a unique combination of features. The porous structure of wet sand creates countless microscopic chambers where molecules could concentrate, shielded from destructive ultraviolet rays yet exposed to the steady drip of radiation. Wave action would have continuously mixed and replenished the organic soup, while the ebb and flow of tides provided rhythmic drying and wetting cycles, both of which can promote chemical bonding. It's as if the beach itself was a vast, natural reactor, tuned to the perfect rhythm for brewing life's precursors. Critics of the radioactive beach hypothesis point out that radiation is a double-edged sword. While it can energize chemistry, it can also shred delicate organic molecules. However, recent studies suggest the balance might tilt in favor of creation over destruction. In simulations, intermittent exposure like that from grains of uranium scattered through sand tends to drive polymerization without completely breaking down the products. The key seems to lie in the dosage. Too much radiation is lethal, but just enough could be transformative. What's fascinating is how this idea connects to broader cosmic patterns. Radioactive elements like uranium weren't born on Earth, they were forged in the explosions of dying stars and delivered here by meteorites. If their decay helped assemble life's molecules, then the story of biology might be intertwined with the life cycles of stars themselves. From supernova to seashores, the universe could have woven its most fragile creations from the fabric of its most violent events. While the radioactive beach hypothesis is still young, it challenges us to rethink our assumptions about life's beginnings. Instead of seeking energy solely from lightning or geothermal heat, perhaps we should look to the quiet, persistent glow of atoms unraveling in the sand. After all, in a universe where even destruction can be a creative force, the boundary between poison and catalyst might be thinner than we think. Deep beneath Earth's surface, where tectonic plates grind and collide, another hidden force might have shaped life's earliest chemistry: supercritical carbon dioxide. Picture a substance that's neither quite a gas nor fully a liquid, a form of CO2 so pressurized and heated that it takes on bizarre, almost magical properties. In this strange state, carbon dioxide becomes a universal solvent, capable of dissolving and transporting organic molecules with eerie efficiency, and in the subduction zones where oceanic plates plunge into the mantle, this supercritical fluid could have been the unseen architect of life's first complex reactions. The magic lies in CO2 behavior under extreme conditions. When temperatures soar above 31 degrees Celsius and pressures exceed 73 times Earth's surface atmosphere, carbon dioxide enters its supercritical phase. Here it gains the density of a liquid while retaining the diffusivity of a gas, allowing it to seep through microscopic cracks in rock like an invisible tide. But more importantly, supercritical CO2 has a unique talent: it can dissolve hydrophobic molecules, like fatty acids and certain amino acids, that ordinary water struggles to handle. This means it could have gathered and concentrated life's building blocks in places where other solvents failed. Lab experiments back this up spectacularly. In 2008, researchers at NASA Jet Propulsion Laboratory recreated subduction zone conditions, subjecting mixtures of water, CO2, and simple organics to crushing pressures and scorching heat. The results were astonishing. Not only did the supercritical CO2 extract and concentrate organic molecules from the surrounding water, but it also facilitated reactions that formed longer chains, like stitching together individual beads into a necklace. Even more striking, these reactions occurred without the need for enzymes or catalysts, relying solely on the brute physics of the environment. Why subduction zones? These geological hotspots are perfect natural laboratories. As one plate dives beneath another, it drags down seawater-soaked minerals and organic sediments, subjecting them to steadily increasing heat and pressure. The descending slab essentially acts like a conveyor belt, feeding raw materials into a reaction chamber where supercritical CO2 can work its chemistry. And unlike hydrothermal vents, which are localized, subduction zones span thousands of kilometers, offering a planet-scale network of potential organic factories. There's another twist: supercritical CO2 doesn't just assemble molecules, it selects them. Because different compounds dissolve to varying degrees in this fluid, the process naturally filters out less stable or reactive molecules, favoring those with the right properties for life's next steps. Imagine a microscopic sorting hat, picking only the most promising candidates for further complexity. Critics might argue that subduction zones are too harsh, their pressures too destructive for delicate organics. Yet recent discoveries of complex molecules in ultra-high-pressure minerals suggest otherwise. Some amino acids and lipids not only survive these conditions, they thrive, using the energy of compression to drive their assembly. And let's not forget, life today thrives in extreme environments, from deep-sea trenches to acidic hot springs. If modern organisms can adapt to such extremes, why couldn't life's precursors have emerged there? The implications ripple far beyond Earth. If supercritical CO2 can forge organic complexity in our planet's depths, then similar processes could be unfolding right now on icy moons like Europa or Enceladus, where subsurface oceans press against rocky mantles. The universe might be full of these hidden crucibles, quietly assembling the pieces of life in places we've only begun to explore. From the crushing darkness of subduction zones to the labs where scientists tease apart these ancient secrets, one thing becomes clear: life's origins might not just be a story of water and light, but of pressure, gas, and the invisible hand of chemistry working in the deep. Some of the most violent events in our planet's history might have been unexpected allies in the story of life's origins. Asteroid impacts, cataclysmic collisions capable of incinerating landscapes and reshaping continents, could have done more than just destroy. The shockwaves from these ancient crashes might have forged the very molecules that made life possible, turning devastation into creative force. Take the Sudbury Basin in Canada, a sprawling geological scar left by an asteroid strike nearly 2 billion years ago. At first glance, it's a monument to destruction, a crater over 60 kilometers wide, but hidden in its rocks lies a clue scientists almost missed: traces of organic carbon, locked deep within the impact-shocked minerals, suggest something extraordinary. The unimaginable pressures and heats generated by the collision could have rearranged simple elements like carbon and nitrogen into more complex structures. It's as if the asteroid's violence acted like a molecular hammer, slamming atoms together with enough force to forge bonds that gentle chemistry couldn't achieve. Laboratory experiment in 2018 brought this theory to life. Researchers used high-powered guns to fire projectiles at speeds rivaling asteroid impacts, targeting mixtures of water, ammonia, and carbon dioxide, ingredients thought to be abundant on early Earth. The results were startling. Not only did the impacts produce amino acids like glycine, but they also generated nucleobases, the informational alphabet of DNA and RNA. These weren't just random byproducts. The shockwaves seemed to prefer biologically relevant molecules, as if the physics of impact selected for life's future needs. What makes impact synthesis so compelling is its sheer universality. Unlike specialized environments like hydrothermal vents or tidal pools, asteroid strikes were a constant in Earth's youth. The late heavy bombardment period, around 4 billion years ago, saw our planet pummeled by space rocks at a rate hundreds of times higher than today. Each impact would have been a localized apocalypse, but also a potential crucible, its shockwaves rippling through the atmosphere and crust, jump-starting chemistry in ways we're only beginning to understand. The process hinges on a phenomenon called shock chemistry. When a massive object strikes Earth, it doesn't just release heat, it generates supersonic pressure waves that propagate through surrounding materials. These waves can stretch and compress molecular bonds in microseconds, forcing reactions that would take millennia under normal conditions. Imagine a sheet of paper crumpled in your hands. Now imagine that paper is a carbon dioxide molecule, and your hands are a shockwave with the power to reshape it into something entirely new. But impacts offer another gift beyond synthesis: delivery. Many asteroids are rich in preformed organic molecules, and while the outer layers burn away during atmospheric entry, the interiors can remain cool enough to preserve their cargo. When these space rocks splashed into Earth's early oceans, they might have dumped their organic payload directly into a warm, watery incubator, like a cosmic UPS driver, unloading packages at life's future doorstep. Critics argue that the extreme heat of impacts would obliterate delicate organics faster than they could form, yet the Sudbury findings and lab experiments suggest otherwise. Shockwaves aren't uniformly destructive. They create intricate gradients of pressure and temperature, with safe pockets where molecules can assemble even as chaos reigns nearby. It's a paradox as old as life itself: creation and destruction, woven together in the same instant. From the scarred basins of Earth to the icy moons of Jupiter, impact synthesis reminds us that life's ingredients might be forged in the universe's most violent workshops. Every crater, no matter how ancient, could be a fossilized testament to the day chemistry took one step closer to biology, not despite the chaos, but because of it. High above the ancient Earth, where the air was thick with methane and nitrogen, an invisible shield might have cradled life's fragile ingredients, a haze of photochemical aerosols. These weren't just any particles, they were organic compounds forged by sunlight, swirling in the upper atmosphere like a cosmic veil. and far from being a passive curtain, this haze could have acted as both a protector and a catalyst, sheltering delicate molecules from the sun's deadly UV rays while quietly assembling them into something greater. We catch glimpses of how this might have worked by looking at Saturn's moon Titan today. Its orange-tinged skies are choked with hydrocarbon aerosols, created when sunlight breaks apart methane molecules high in the atmosphere. These tiny particles don't just hover, they clump together, growing heavier until they drift down like organic snow, coating the moon's surface with a layer of potential chemistry. On early Earth, a similar process could have unfolded, with methane likely more abundant in our planet's youth. Ultraviolet light would have sliced through those molecules, creating radicals and ions that quickly recombined into more complex organics. Over time, these compounds would have aggregated into aerosols, forming a persistent haze layer. But here's where it gets fascinating. Laboratory simulations reveal that these aerosols aren't just passive byproducts, they're active chemical factories. When scientists recreate early atmospheric conditions in sealed chambers, irradiating methane-nitrogen mixtures with UV lamps, the resulting haze particles turn out to be packed with amino acids and nucleobases. It's as if the haze itself is a floating laboratory, synthesizing life's precursors right in the sky, and unlike the surface where waves or volcanic heat could scatter molecules, the haze offers stability. Particles can linger for years, slowly growing more complex as they absorb additional gases or react with one another. Perhaps most crucially, this photochemical shield solves one of the biggest puzzles in origin of life research, the UV problem. Early Earth had no ozone layer, meaning the sun's unfiltered ultraviolet radiation would have shredded unprotected organic molecules within hours, but aerosols absorb UV light like a sponge, converting its destructive energy into chemical bonds. Picture a parasol made of carbon and nitrogen, one that doesn't just block the sun, but uses its power to weave intricate molecular patterns. There's another advantage to this high-altitude chemistry. Unlike hydrothermal vents or tidal pools, which are localized, atmospheric hazes would have enveloped the entire planet. Every rainstorm would have washed aerosol particles down into oceans and lakes, delivering a steady drizzle of preformed organics to environments below. Some models suggest this could have created concentrated, hotspots where molecules accumulated, like nutrient-rich patches in an otherwise sparse ocean. Yet the theory isn't without its challenges. Would enough organic material have survived the journey from sky to surface? Experiments suggest yes, especially if the particles clumped into larger aggregates before falling. And while Titan's haze is dominated by simple hydrocarbons, Earth's warmer, wetter atmosphere might have driven the chemistry further, toward nitrogen-rich compounds like adenine or uracil. What's striking is how this idea turns conventional wisdom on its head. Instead of life's building blocks forming in the depths of oceans or the pores of rocks, they could have been raining down from the skies all along. From the orange gloom of Titan to the primordial mists of Earth, photochemical aerosols remind us that sometimes the most unlikely places, even the empty expanse of an atmosphere, can become cradles for chemistry's greatest masterpiece. Deep in the scalding waters around hydrothermal vents, where black smoke billows from towering mineral chimneys, an unassuming mineral might have unlocked one of life's greatest secrets. Iron sulfide, commonly known as fool's gold or pyrite, isn't just a glittering geological curiosity. According to chemist Günther Wechtersheuser's groundbreaking theory, this humble compound could have been the cornerstone of life's earliest metabolism, acting as both a catalyst and an energy source in the absence of enzymes or cells. Wechtersheuser's vision, dubbed the iron-sulfur world hypothesis, flips traditional origin of life thinking on its head. Instead of genes or membranes coming first, he proposed that simple chemical reactions on pyrite's metallic surface could have formed a primitive metabolic network, a kind of molecular engine that ran on geochemistry rather than biology. Here's how it might have worked. Pyrite forms naturally in hydrothermal vents when iron reacts with hydrogen sulfide, releasing tiny bursts of energy. Miller-Urey realized this energy could power other reactions, like carbon dioxide bonding with hydrogen to form organic molecules. The pyrite's crystalline surface, with its grid of iron and sulfur atoms, would have acted like a molecular scaffold, holding reactants in place while the energetics of sulfide oxidation drove them toward greater complexity. Recent experiments lend startling support to this idea. Scientists simulating vent conditions in high-pressure reactors have observed pyrite surfaces facilitating reactions that produce acetic acid, a simple but crucial molecule in modern metabolism. Even more impressively, when researchers added nickel to the mix, they found it could catalyze the formation of peptides, short chains of amino acids. This suggests that vent minerals didn't just provide energy, they might have actively guided chemistry toward biological complexity, but the iron-sulfur world's real magic lies in its potential for self-sustaining cycles. Imagine a feedback loop where the energy released by pyrite formation fuels more organic synthesis, which in turn alters the local environment to promote further reactions. Over time, these cycles could have grown increasingly intricate, eventually crossing the blurry line between geochemistry and biochemistry. It's a concept echoed in modern cells, where iron-sulfur clusters remain embedded in the heart of critical enzymes, almost like molecular fossils of this ancient partnership. Critics argue that pyrite's reactivity is a double-edged sword. While it can build molecules, it can also degrade them under the same harsh vent conditions. Yet hydrothermal systems aren't static. Temperature gradients and mineral porosity create microenvironments where delicate products might have been preserved long enough to take the next evolutionary step. And let's not forget, life today thrives in these very vents, their inhabitants still relying on iron and sulfur chemistry to harvest energy. Miller-Urey's theory does more than suggest a location for life's origins, it redefines what life is. By framing metabolism as a natural outgrowth of planetary geology, it bridges the gap between Earth's lifeless youth and the vibrant biosphere we know. From the glint of pyrite in a rock to the iron-rich core of every cell, the echoes of this process might be written deep into the fabric of biology itself. Among the countless chemical reactions that could have shaped life's beginnings, one stands out for its eerie elegance: the foremost reaction. Picture a simple molecule, formaldehyde, drifting in a shallow pool of alkaline water. Left alone, it might seem unremarkable, but under the right conditions, something extraordinary happens. These molecules begin linking together, not randomly, but with a peculiar sense of order, forming sugars like ribose, the very backbone of RNA, the molecule many scientists believe came before DNA in the earliest forms of life. It's as if the universe had a hidden recipe for biology's building blocks, written in the language of carbon and oxygen. The magic of this reaction lies in its simplicity. Formaldehyde, a compound so basic it's found in interstellar space, can spontaneously polymerize in alkaline solutions, creating a cascade of sugar molecules. The process starts with two formaldehyde units combining to form glycolaldehyde, a simple sugar. From there, the reaction spirals outward, adding more formaldehyde units like beads on a string, eventually yielding a mix of sugars including ribose. What's astonishing is that this isn't some rare, lab-only phenomenon. Researchers have recreated it under conditions mimicking early Earth's alkaline lakes, where volcanic activity or mineral leaching could have created the perfect alkaline environment. But there's a catch: the foremost reaction is notoriously messy, producing a jumble of sugars, not just the ribose critical for RNA. That's where borate minerals enter the story. These naturally occurring compounds found in ancient dry lake beds have a remarkable talent for stabilizing ribose. When borate ions are present in the reaction mix, they latch onto ribose molecules, shielding them from degradation while other sugars break down. It's a molecular version of natural selection, where borate acts as a filter, preserving the exact sugar life would later depend on. The implications for the RNA world hypothesis are profound. If ribose could form and accumulate in alkaline, borate-rich pools, then the gap between simple chemistry and genetic molecules narrows dramatically. RNA, with its ability to both store information and catalyze reactions, might have emerged from this sugary broth, kickstarting the transition from chemistry to biology. Some researchers even suggest these alkaline environments could have acted as primordial nurseries, where borate-stabilized ribose teamed up with other prebiotic molecules to form the first RNA strands. Yet the foremost reaction isn't without its skeptics. Some argue that the conditions required just the right alkalinity, formaldehyde concentration, and borate presence might have been too finicky for widespread occurrence. Others point out that while ribose forms, it's still a long way from a functional RNA strand, but recent discoveries keep breathing life into this theory. In 2019, scientists found that mineral surfaces like clay could further refine the reaction, nudging it toward biologically relevant outputs. And let's not forget, borate minerals aren't rare. They're abundant in places like Death Valley, suggesting that if early Earth had similar geology, the ingredients for this sugar factory were everywhere. What's mesmerizing about the foremost reaction is how it blurs the line between randomness and destiny. A molecule as simple as formaldehyde, given the right push, seems almost predisposed to assemble into life's essential sugars. Whether this process unfolded in steaming alkaline springs or sunlit pools edged with borate crystals, it hints at a universe where the path from chemistry to biology isn't just possible, it's woven into the very fabric of matter. Next time you see sugar dissolve in your coffee, consider this: the same sweetness might have once been the spark that set life in motion. Beneath our feet, where the weight of the planet crushes rock into strange new forms, another chapter in life's origin story might be unfolding. While we often picture life beginning in sunlit pools or steamy volcanic vents, some scientists argue the real action happened much deeper, where pressures are so intense they can warp the very rules of chemistry. This is the realm of deep Earth synthesis, a theory suggesting that the crushing embrace of Earth's mantle could have forged life's building blocks in total darkness, far from oceans or sunlight. The key to this idea lies in an unassuming tool, the diamond anvil. Smaller than a thimble, this device uses the hardest natural material on Earth to recreate the insane pressures found hundreds of kilometers below the surface. When researchers squeeze simple molecules like carbon dioxide, water, and nitrogen between these diamond jaws, something remarkable happens. Under pressures exceeding 50,000 times Earth's atmosphere, equivalent to the weight of several elephants balanced on a sugar cube, these inert gases begin reacting, forming complex organics like methane, ethane, and even amino acids. It's as if the pressure itself becomes a chemical alchemist, forcing bonds to rearrange against their natural tendencies. One groundbreaking experiment in 2019 took this further. Scientists subjected a mixture of iron, carbon, and water to mantle-like conditions, mimicking the environment near Earth's core mantle boundary. The result: not just simple organics, but acetylene and pyruvate molecules central to modern metabolic pathways. This suggests that deep Earth isn't just a passive blender of elements, it could be a factory for prebiotic chemistry, operating on scales and timelines dwarfing surface processes. But how would these molecules ever reach the surface? Here's where geology offers a clue. Subduction zones, where tectonic plates dive into the mantle, act like conveyor belts, dragging water and carbon-rich minerals downward. Meanwhile, volcanic plumes and mid-ocean ridges spit material back up. Over billions of years, this planetary circulation could have transported mantle-synthesized organics into shallower environments, where they joined the primordial soup. It's a slow-motion recycling system, with life's ingredients riding tectonic currents between destruction and rebirth, critics raise valid objections. Could delicate organics survive the ascent through scorching mantle plumes? Proponents point to microscopic pockets in minerals like olivine, which might shield molecules during their journey. Others argue that without a way to concentrate these molecules, they'd disperse into useless dilution, yet recent work on hydrothermal systems shows how thermal gradients can naturally funnel organics into localized hotspots, solving the concentration problem. The implications stretch beyond Earth. Icy moons like Europa and Enceladus have subsurface oceans crushed under thick ice shells environments not unlike Earth's deep mantle. If high-pressure chemistry works here, why not there? From the crushing depths of our planet to the hidden oceans of distant worlds, the universe might be quietly assembling life's toolkit in places we've barely begun to explore. The deeper we look, the more we realize, life's origins might not be a surface story at all, but a tale written in the unyielding darkness below. At the freezing edges of the early Earth, where glaciers met the sea, another surprising recipe for life's molecules might have been quietly unfolding. While we often focus on heat as the engine of chemical change, there's growing evidence that cold could have been just as creative. Picture a world where organic compounds don't dissolve in warm water. Instead, they're trapped inside tiny ice crystals, squeezed together with increasing intensity as temperatures plummet. This process, known as freeze concentration, turns ice into a molecular vise, forcing reactions that would never occur in the spacious freedom of liquid water. The European Space Agency's experiments reveal just how powerful this icy chemistry can be. In simulations mimicking the frigid conditions of space or Earth's ancient polar regions, scientists sealed simple molecules like ammonia and formaldehyde in ice samples cooled to -20 degrees Celsius. Left for weeks in this deep freeze, something astonishing happened. The ice's crystalline structure expelled impurities as it formed, herding the trapped molecules into microscopic pockets where they reached staggering concentrations, up to 1,000 times denser than in open water. Within these cramped, ultra-cold chambers, the molecules had no choice but to react, spontaneously forming amino acids like glycine without any added energy. It's as if the ice itself acted as both reactor and catalyst, its very structure guiding chemistry toward biological complexity. But why does freezing drive such efficient synthesis? The secret lies in what chemists call the brine rejection effect. As water turns to ice, it excludes salts and organic compounds, creating ultra-concentrated liquid veins between ice grains. These briny channels become chemical hotspots, where molecules collide far more frequently than they would in a dilute ocean. Add to this the fact that low temperatures stabilize fragile intermediates molecules that would instantly fall apart in warmth, and you've got an environment where complexity can build gradually, protected by the ice's frozen embrace. Real-world observations back this up. In Antarctica's McMurdo Dry valleys, researchers have found amino acids in ice cores, their concentrations spiking precisely where freeze-thaw cycles are most intense. Even more compelling, comets, those icy remnants of the solar system's birth, are now known to harbor glycine, detected by missions like Rosetta. If freezing space can manufacture life's ingredients, why not Earth's ancient ice sheets? The polar ice theory flips conventional wisdom on its head. Instead of life's precursors requiring volcanic heat or lightning strikes, they might have been painstakingly assembled in the quiet cold, one frozen winter at a time. From the glaciers of the early Earth to the icy crusts of moons like Europa, the universe seems to whisper that life's chemistry isn't picky, it'll work with heat or cold, whichever's available. Sometimes progress doesn't melt barriers, it freezes them into place. Winding through Yellowstone National Park today, the acidic hot springs and bubbling mud pots aren't just geological curiosities, they're windows into a process that might have turbocharged life's earliest chemistry. These geothermal fields, with their rhythmic cycles of flooding and evaporation, could have acted as natural laboratories where molecules didn't just form but grew into long, complex chains. The secret lies in the dance between wet and dry. When mineral-rich water floods a hot spring, it dissolves and mixes organic compounds. As the water evaporates under the scorching sun or geothermal heat, those compounds are left behind, squeezed together like commuters in a shrinking elevator. This isn't just concentration, it's a chemical pressure cooker, where molecules are forced into reactions that would rarely happen in a more relaxed, watery environment. Take the work of researchers at the University of Washington, who recreated these conditions in the lab. They filled shallow pools with nucleotides, the building blocks of RNA, and subjected them to cycles of wetting and drying. In just a few dozen cycles, something remarkable unfolded. The nucleotides linked into chains over 50 units long, a critical step toward the complexity needed for genetic information. What's striking is how closely this mirrors Yellowstone's acidic springs, where minerals like silica and sulfur add another layer of catalytic power. The acidic environment isn't just a bystander, it can stabilize these fragile polymers, preventing them from unraveling long enough to take on biological roles. But geothermal fields offer more than just wet-dry cycles. Their temperature gradients are like a molecular obstacle course. As water evaporates from the edges of a hot spring, the remaining solution becomes hotter and more concentrated, driving reactions even faster. Meanwhile, mineral surfaces like the jagged edges of volcanic rock provide scaffolding, aligning molecules in ways that favor bonding. It's a perfect storm of conditions: heat to energize reactions, acidity to preserve the products, and rhythmic drying to keep the process moving forward. Critics might argue that acidic hot springs are too harsh for delicate organics, but life today thrives in these very environments. From Yellowstone steaming pools to deep-sea hydrothermal vents, extremophiles prove that acidity and heat aren't deal breakers, they're catalysts. And the geological record suggests early Earth was littered with similar geothermal fields, their cycles ticking like clocks across millennia, each turn of the wheel nudging chemistry closer to biology. The implications stretch beyond our planet. Mars's ancient hot springs, like those in Columbia Hills, show signs of similar wet-dry cycling. If geothermal fields on Earth could have driven polymerization, why not elsewhere? From the bubbling cauldrons of Yellowstone to the fossilized springs of distant worlds, the universe might have been using the same simple recipe: add water, remove water, repeat. Sometimes life's greatest leaps forward come not from grand, singular events, but from the patient, persistent rhythm of a planet breathing in and out. Earth's magnetic field might seem like an unlikely player in the origin of life, but its invisible influence could have been the silent architect behind one of biology's most puzzling quirks: chirality. Picture molecules as tiny mirror images, identical in composition but opposite in structure, like left and right hands. Life, for reasons still unclear, overwhelmingly prefers one version over the other. DNA twists right, amino acids lean left. This bias, known as homochirality, is so fundamental that scientists have long wondered how it emerged from a supposedly symmetrical universe. The answer might lie in the subtle interplay between Earth's early magnetic field and the quantum properties of molecules. A groundbreaking study in 2022 revealed something extraordinary. When certain chiral molecules are exposed to a magnetic field, their electrons behave differently depending on which mirrored form they take. This tiny asymmetry, amplified over time, could have tilted the scales toward one dominant version. Think of it like a cosmic coin toss, where magnetism subtly weighted the odds. Early Earth's magnetic field, though weaker than today's, was still a constant presence, a quiet force nudging molecules toward uniformity with every passing storm or tidal shift. But how could something as intangible as magnetism leave such a concrete mark? The secret lies in something called the chiral-induced spin selectivity effect. Electrons moving through a chiral molecule aren't just carrying charge, they're also spinning, and their spin direction can be influenced by the molecule's handedness. When aligned with Earth's magnetic field, one version of a molecule might stabilize slightly better than its mirror image, creating a feedback loop where the winner accumulates while the other fades. It's like a molecular version of survival of the fittest, with magnetism as the invisible selector. Lab experiments have brought this theory to life. Researchers at the Weizmann Institute observed that when chiral molecules were subjected to magnetic fields under prebiotic conditions, their stability diverged sometimes by as much as 10%. Over millennia, that slight edge could have snowballed into the overwhelming bias we see today. Even more compelling, similar effects have been detected in meteorites, where amino acids show slight chiral imbalances that align with the magnetic fields of their parent asteroids. Critics argue that Earth's early magnetic field was too weak to drive such a dramatic shift, yet quantum effects don't require brute force, just consistency. And with the entire planet acting as a slow, steady magnet, even a minuscule preference could have cascaded into dominance. From the swirling currents of Earth's molten core to the delicate dance of electrons in a primordial molecule, the stage was set for magnetism to leave its mark on life's blueprint. What's fascinating is how this idea bridges the colossal and the microscopic, a planet-scale force shaping the very molecules that would one day build cells, organisms, and minds. It's a reminder that life's origins aren't just about chemistry or energy, they're about the hidden threads connecting the physics of the cosmos to the quirks of biology. Whether gazing at the auroras or studying the twist of a DNA strand, we might be seeing echoes of the same ancient magnetic whisper that guided life's first steps. High above the storm clouds, where Earth's atmosphere thins into the ionosphere, another invisible force could have been quietly crafting life's precursors, corona discharge. This isn't the crackling lightning we see during thunderstorms, but something far subtler, a shimmering veil of plasma, energized by solar radiation and cosmic rays, dancing at the edge of space. In this electrified frontier, simple gases like nitrogen and methane might have transformed into nitriles, a class of nitrogen-rich compounds that serve as critical stepping stones to amino acids and DNA. The process hinges on a peculiar quirk of plasma chemistry. Unlike the brute force energy of lightning, corona discharge generates a gentler, more sustained flow of electrons. These particles collide with atmospheric molecules, stripping away electrons and creating reactive ions. Nitrogen, normally reluctant to bond, becomes far more sociable in this state, readily linking with carbon to form cyanide and other nitriles. It's as if the upper atmosphere becomes a cosmic chemistry set, with plasma acting as the invisible hand guiding reactions too delicate for Earth's turbulent lower layers. Jupiter offers a striking parallel. NASA Juno spacecraft has detected vast networks of lightning in the gas giant's upper atmosphere, where ammonia and water vapor swirl in violent storms. But more intriguing are the elves and sprites, faint, ephemeral plasma discharges that flicker above the storm clouds. These phenomena, similar to Earth's corona discharge, are now thought to produce hydrogen cyanide and other nitriles in Jupiter's stratosphere. If the same process unfolds there, why not on a younger, more volatile Earth? Lab experiments back this idea. In 2021, researchers at the University of Georgia recreated upper atmosphere conditions in a plasma chamber, filling it with nitrogen, methane, and water vapor, gases thought to dominate Earth's early air. After days of sustained discharge, the mixture teemed with nitriles, including formanitrile and acetonitrile. Even more compelling, these compounds formed most efficiently at altitudes where solar UV and cosmic rays would have supercharged the plasma, suggesting that corona discharge wasn't just possible, it was inevitable. But here's where the theory gets truly elegant. Unlike lightning strikes, which are localized and fleeting, corona discharge would have blanketed the entire planet, a continuous, planet-wide synthesis machine. Every high-altitude wind shear or solar flare could have intensified the effect, raining nitriles down into the oceans below, and because the upper atmosphere is cold, these fragile molecules would have survived their descent, shielded from the destructive heat that plagues lower-altitude chemistry. Critics point out that nitriles alone don't equal life, they're just one piece of the puzzle, yet their versatility is undeniable. In the presence of water and minerals, nitriles can rearrange into adenine, a key component of DNA, or glycine, the simplest amino acid. What makes corona discharge special isn't just the molecules it creates, but the scale. While hydrothermal vents or tidal pools might excel at local synthesis, the ionosphere could have been a global distributor, ensuring no corner of the planet went without life's raw materials. From the electric blue flickers of Jupiter's stratosphere to the invisible plasma rivers of Earth's ancient skies, corona discharge reminds us that life's origins might not be grounded in the familiar. Sometimes the most transformative chemistry happens where we least expect it, not in the warmth of sunlit pools or the depths of volcanic fissures, but in the silent, shimmering frontier between atmosphere and space. The violence of a meteorite impact seems like pure destruction, but within its fiery heart, chemistry might have been working at breakneck speed to build rather than break. When a massive asteroid slams into Earth, the collision doesn't just carve craters, it vaporizes rock, metal, and even atmospheric gases, creating a superheated plume of ionized chaos. As this inferno expands and cools, something counterintuitive happens. The very energy that obliterated solid matter can reassemble its fragments into new, astonishingly complex forms. The Chicxulub crater, the infamous dinosaur killer impact site, offers startling clues about this process. Researchers analyzing its ancient layers found traces of Fulleren's buckyball-shaped carbon molecules that only form under extreme heat and pressure. But these weren't just random byproducts of destruction. Their nested, cage-like structures hinted at a hidden order emerging from the impact's fury. Lab experiments reveal why this phenomenon occurs. When scientists simulate asteroid strikes using high-speed projectiles, the resulting vapor plume contains not just broken molecular shards, but stitched-together hybrids. Silicates from the ground bond with atmospheric nitrogen, forming cyanide compounds. Carbon atoms link into chains and rings, creating polycyclic aromatic hydrocarbons. Even amino acids like glycine appear, as if the impact's violence forces atoms into life-friendly configurations against their usual reluctance. The key lies in rapid quenching. The plume's outer layers cool so fast that newly formed molecules don't have time to fall apart, freezing them into unexpected complexity, like a chemical snapshot of the chaos. But Chicxulub isn't the only smoking gun. The Sudbury crater in Canada, forged by an impact 2 billion years ago, harbors even more direct evidence. Hydrothermal systems within its fractured rocks concentrated nickel and iron, elements that could have catalyzed further organic synthesis long after the initial strike. Here's the twist. These metals didn't just passively assist reactions, they acted like molecular shepherds, guiding carbon and nitrogen toward biologically relevant arrangements. Imagine a blacksmith's forge, where hammer blows don't just shape metal but transmute it into something entirely new. The implications ripple beyond Earth. Mars's ancient craters like Gale or Jezero show signs of similar post-impact hydrothermal activity. If vapor plume chemistry worked here, why not on the red planet during its wetter, warmer youth? Even more tantalizing, this process might solve a paradox: how life's delicate building blocks could emerge from the very events that seem designed to erase them. From the ashes of cataclysm, the universe appears to have woven a backdoor, a way to turn annihilation into creation. Meteorite impact vapor doesn't just rewrite the story of life's ingredients, it collapses the line between endings and beginnings. Every crater, no matter how violent its birth, might secretly double as a crucible, a place where the universe's most destructive forces become, against all odds, its most ingenious chemists. Black smokers, those towering undersea chimneys speaking superheated, mineral-rich plumes, might seem like unlikely cradles for life's chemistry, but hidden within their porous walls lies a secret architecture that could have turned these geological formations into nature's earliest laboratories. Recent expeditions with advanced submarine drones reveal something astonishing. The intricate networks of microscopic channels inside these chimneys don't just vent hot water, they act as a labyrinth of natural reaction chambers, each pore perfectly sized to trap and concentrate organic molecules while shielding them from the crushing pressures and chaotic currents of the deep ocean. The key to this process lies in the chimney's unique mineral composition. Made mostly of iron and sulfur-rich compounds like pyrrhotite, these structures aren't solid rock, they're more like mineral sponges, riddled with interconnected voids measuring mere micrometers across. When superheated fluids loaded with hydrogen sulfide and dissolved metals surge through these narrow passageways, something extraordinary happens. The confined spaces force molecules into close proximity, while the mineral surfaces act as catalysts, lowering the energy barriers for key reactions. It's as if each pore becomes a microscopic flask, where carbon dioxide and hydrogen can link up to form formate, a simple but crucial organic compound. Cutting-edge drone footage from the mid-Atlantic ridge shows this chemistry in action. High-resolution thermal scans reveal temperature gradients varying wildly across a single chimney, from scorching 350 degrees Celsius near the venting throat to a tepid 50 degrees at the outer edges. This isn't just random variation, it's a precision-engineered landscape where different reactions can occur simultaneously in adjacent pores. Imagine a vast underground city, where each district specializes in a different step of molecular assembly. One alleyway produces aldehydes, the next stitches them into alcohols, and a third fuses those into fatty acids. The chimney isn't just a structure, it's an ecosystem of interconnected chemistry. But here's the twist that submarine drones helped uncover: these systems aren't static. As new mineral layers deposit on the chimney walls, older pores collapse, creating a dynamic cycle where organic products get periodically released into the surrounding water, like a molecular conveyor belt delivering prebiotic ingredients to the ocean. Autonomous samplers deployed near active smokers have detected concentrated plumes of pyruvate and acetyl-CoA, molecules central to modern metabolism, drifting away from the vents. This suggests black smokers didn't just cook life's ingredients, they packaged and distributed them. Critics once argued that vent environments were too harsh for delicate organics, but the drone findings turned that assumption on its head. The porous matrix acts as a shock absorber, smoothing out sudden temperature or pressure changes that would shred unprotected molecules. And the latest shocker: some chimneys exhibit electrical conductivity, with charge differences between their inner and outer surfaces creating natural proton gradients eerily similar to how modern cells generate energy. From their mineral pores to their electrochemical properties, black smokers appear fine-tuned for the alchemy that bridges geology and biology. What began as curious formations on the ocean floor now look like cosmic-scale experiments in molecular architecture, a billion-year-old blueprint for how chemistry might self-organize toward life, written in stone, sulfur, and searing heat. And with every new dive, our robotic explorers bring back evidence that these alien towers might not be so alien after all, but the very crucibles where Earth discovered how to turn rock and water into biology. The sun, that blazing furnace at the center of our solar system, might have been an unexpected chemist in the story of life's origins, not just with its light, but with its wind. Solar wind, that relentless stream of charged particles racing outward at nearly 1,000,000 miles per hour, has long been known to erode surfaces and strip atmospheres. But recent experiments reveal something far more surprising. Those same particles can act like molecular sculptors, carving simple ices into complex organic molecules, even in the frigid depths of space. Take the asteroid Ryugu, where samples returned by Japan's Hayabusa 2 mission contain traces of glycine, the simplest amino acid embedded in its surface layers. At first, scientists assumed these organics formed deep within the asteroid's interior, shielded from radiation, but lab simulations tell a different story. When researchers at the University of Sherbrooke bombarded ice mixtures of water, ammonia, and carbon dioxide with protons mimicking solar wind, glycine formed within days. The mechanism is as elegant as it is unexpected. The proton's energy breaks apart the ice molecules, creating reactive fragments that quickly recombine into more complex structures. It's like a cosmic game of molecular billiards, where solar wind provides both the cue stick and the force to rearrange the pieces. What makes this discovery so revolutionary is its universality. Asteroids like Ryugu are time capsules from the solar system's infancy, and if solar wind could turn their icy surfaces into organic factories, the implications stretch far beyond Earth. Europa, Jupiter's ice-cloaked moon, is constantly bathed in even fiercer radiation as it plows through the planet's magnetic field. The same process that created glycine on Ryugu could be unfolding right now on Europa's surface, where solar and Jovian radiation might be transforming its cracked, icy crust into a sprawling organic workshop. But there's a twist to this solar-powered chemistry. Unlike hydrothermal vents or tidal pools, where reactions depend on local conditions, solar wind synthesis operates on a galactic scale. Every icy body exposed to starlight, whether a Kuiper belt object or a comet drifting near the outer solar system, could be participating in this quiet, relentless chemistry. The universe, it seems, doesn't need gentle environments to build life's ingredients. Sometimes all it takes is a storm of charged particles and patience measured in eons. Critics argue that glycine alone isn't enough to jumpstart biology, and they're right, but solar wind doesn't stop there. Follow-up experiments show that prolonged exposure can produce more complex molecules like alanine and even sugars. And because these compounds form on the surface, they're perfectly positioned to hitch rides on comets or meteoroids, seeding young planets with pre-made organic kits. From the sun-scorched face of an asteroid to the radiation-drenched plains of Europa, solar wind synthesis reshapes our understanding of life's potential distribution. It suggests that the raw materials for biology aren't just hiding in hidden oceans or deep-sea vents. They might be plastered across the frozen surfaces of countless worlds, waiting for the right conditions to thaw them into action. The next time you feel the warmth of sunlight in your skin, remember, that same star might be quietly assembling the pieces of life elsewhere in the cosmos, one proton at a time. Picture a world where the snow isn't made of water, but of acetylene, a colorless gas that, under the right conditions, crystallizes into delicate flakes and drifts silently through alien skies. This isn't science fiction. It's a phenomenon scientists believe could be happening right now on Saturn's moon Titan, and it might hold clues to how life's building blocks were delivered to early Earth. In the bone-chilling cold of Titan's upper atmosphere, where temperatures plunge to -180 degrees Celsius, acetylene doesn't just linger as a gas, it condenses into tiny ice particles, creating a surreal form of precipitation. These aren't the snowflakes we know, they're hydrocarbon crystals, potentially carrying organic molecules like a cosmic conveyor belt from the atmosphere to the surface. The magic begins high in Titan's stratosphere, where sunlight triggers reactions between methane and nitrogen, producing a soup of complex organics. Among them, acetylene forms readily, and because it's heavier than other atmospheric components, it slowly sinks. As it descends into colder layers, something extraordinary happens. The gas transitions directly into solid ice, bypassing the liquid phase entirely, a process called deposition. Lab simulations at NASA Glenn Research Center have recreated these conditions, chilling acetylene vapor until it spontaneously crystallizes into micrometer-sized particles. Under Titan-like pressures, these particles clump together into fractal structures eerily reminiscent of Earth's snowflakes, but with a twist. Their surfaces are sticky, coated with tholins, tar-like organics forged by ultraviolet radiation. Here's where the theory gets tantalizing. As acetylene snowflakes fall, they act like microscopic sponges, scavenging other organic molecules from the atmosphere. Studies using mass spectrometers have shown that these flakes can absorb compounds like hydrogen cyanide and cyanocetylene, molecules that are critical precursors to amino acids and nucleobases. By the time the snow reaches Titan's surface, it's no longer just acetylene, it's a concentrated payload of prebiotic chemistry, piling up in dunes or dissolving into methane lakes. The implications for early Earth are profound. While our planet was never as cold as Titan, there's growing evidence that acetylene could have played a similar role in its ancient, carbon-rich atmosphere. During the Archean eon, when the sun was dimmer and atmospheric methane levels higher, acetylene snow might have formed at high altitudes, especially during periods of global cooling. As these flakes drifted downward, they could have delivered organics to Earth's surface far more gently than comet impacts or lightning strikes, preserving delicate molecules that would otherwise be destroyed by heat or radiation. Recent climate models of early Earth support this idea. Simulations run by the University of Chicago show that even brief cooling episodes triggered by volcanic winters or asteroid impacts could have created localized acetylene snow events, particularly over polar regions. Unlike water snow, which would melt and dilute organics, acetylene snow would sublimate slowly, leaving behind concentrated deposits on cold ground or ice sheets. Over millennia, these deposits might have accumulated in sheltered areas, creating reservoirs of organic material ready for the next step in life's chemical evolution. Critics point out that Earth's atmosphere was likely too warm for persistent acetylene snow, but Titan teaches us that chemistry doesn't need permanence, just opportunity. Even transient snow events repeated across millions of years could have amassed enough material to matter, and let's not forget, acetylene isn't the only player. On Titan, benzene and ethane snow also fall, each carrying its own suite of organics. Early Earth might have hosted a diverse precipitation system, with different snows delivering different molecular tools to the surface. From the hydrocarbon blizzards of Titan to the faint whispers of acetylene frost on a primordial Earth, this theory reshapes how we think about life's delivery system. Sometimes the quietest processes, the gentle drift of snow in an alien sky, hold the loudest echoes of our own origins. The universe doesn't always build life with fireworks. Sometimes it lets the flakes fall where they may. Phosphorus is the unsung hero of life's chemistry, the quiet backbone of DNA, the spark plug of cellular energy, and a linchpin in the structure of every living cell. But here's the puzzle: while phosphorus is essential, it's notoriously scarce in forms that life can easily use. On early Earth, most phosphorus was locked away in inert minerals like apatite, stubbornly insoluble and biologically useless. This is the so-called phosphorus problem, a glaring gap in our understanding of how life's molecular machinery could have gotten started without access to this critical ingredient. Enter schrebersite, a metallic phosphorus mineral found in iron-rich meteorites. Unlike its earth-bound cousins, schrebersite is far more reactive, dissolving readily in water and releasing phosphorus in forms that can bond with organic molecules. The discovery of this mineral in ancient meteorites has sparked a revolutionary idea. What if the phosphorus needed for life's origins didn't come from Earth at all, but rained down from space. The evidence is compelling. In 2013, researchers analyzing the 4.5 billion-year-old Samchin meteorite found schreibersite grains laced with phosphides compounds that, when exposed to water, transform into phosphites and pyrophosphates. These aren't just any phosphorus compounds, they're the precise intermediates needed to build ATP, the universal energy currency of cells. Even more striking, lab experiments show that schreibersite can catalyze the formation of phosphorylated sugars, the backbone of RNA, under conditions mimicking early Earth's lakes and oceans. It's as if these meteorites were preloaded with life's starter kit, delivering not just raw materials but the chemical spark to assemble them. But the story doesn't end there. Schreibersite's reactivity might solve another mystery: how early biochemistry overcame energy barriers. Modern cells rely on ATP to power reactions, but prebiotic chemistry had no such luxury. Schreibersite, when corroding in water, releases electrons, creating natural redox gradients that could have driven primitive metabolic cycles long before enzymes evolved. Picture a microscopic battery embedded in a meteorite fragment, quietly energizing the chemistry around it. Critics argue that meteoritic phosphorus alone couldn't have sustained life's rise. After all, how much could have actually survived Earth's turbulent youth? Recent geochemical models suggest more than we'd think. During the late heavy bombardment, phosphorus-rich meteorites may have delivered up to 10,000 times more soluble phosphorus than Earth's native sources. And because schreibersite tends to concentrate in metallic meteorites, which resist atmospheric ablation better than stony ones, much of its payload could have reached the surface intact. The implications ripple beyond our planet. Mars, with its thinner atmosphere and wealth of iron meteorites, might have experienced an even richer schreibersite infusion, raising tantalizing questions about phosphorus availability for potential Martian life. From the metallic cores of asteroids to the shallow ponds of early Earth, this overlooked mineral could have been the silent enabler of biology's first whispers. Sometimes the key to life's greatest mysteries isn't a blazing bolt of energy or a dramatic geological event, but a humble space rock, carrying the one element Earth couldn't provide on its own. At the frigid fringes of chemistry, where traditional reactions grind to a halt, quantum mechanics might be quietly rewriting the rules of how life's building blocks formed. In the icy depths of space or the frozen pores of early Earth's glaciers, temperatures often drop so low that molecules should be locked in immobility, unable to overcome the energy barriers needed for reactions. Yet somehow, complex organics still emerge in these environments. The answer could lie in a bizarre quantum phenomenon called tunneling, where particles cheat the classical rules of physics by vanishing through barriers rather than climbing over them. A groundbreaking study in 2023 at the University of Leeds revealed just how powerful this effect can be. Researchers trapped formaldehyde molecules, a simple compound abundant in interstellar space, inside matrices of solid argon chilled to near absolute zero. At these temperatures, molecules should be frozen in place, their bonds too stiff to bend or break, but when the team zapped the ice with infrared lasers, something impossible happened. The formaldehyde molecules began reacting with neighboring hydrocarbons, forming glycolaldehyde, a sugar critical for RNA synthesis, without ever gaining enough thermal energy to surmount the reaction barrier classically. The only explanation: quantum tunneling had allowed hydrogen atoms to teleport through the energy wall, enabling bonds to rearrange in the quantum shadows. What's even more astonishing is the speed. These reactions occurred within picoseconds, defying the conventional wisdom that cold chemistry must be sluggish. The implications ripple across astrochemistry. In the frozen clouds between stars, where temperatures hover around 10 degrees above absolute zero, tunneling could explain the detection of complex molecules like ethanol and glycolaldehyde by radio telescopes. These aren't just passive relics of warmer environments, they might be actively forming in the cold, powered by quantum weirdness rather than heat, but quantum tunneling isn't limited to deep space. On early Earth, icy crusts at the poles or high-altitude glaciers could have hosted similar reactions. Experiments simulating these conditions show that tunneling isn't random, it favors specific pathways that align with life's chemistry. For example, when hydrogen bonds shift during tunneling, they tend to stabilize intermediates that coincidentally resemble metabolic precursors. It's as if quantum mechanics has a subtle bias toward biologically useful configurations, even in the absence of biological selection. Critics argue that tunneling alone can't explain life's complexity. After all, most tunneling events are isolated, single-step reactions, yet 2023 models from the Max Planck Institute suggest otherwise. When tunneling reactions occur within confined spaces like the microscopic cracks in ice or mineral pores, the products can accumulate and interact, creating cascades of complexity. One tunneling event might produce glycolaldehyde, which then tunnels into another reaction, building toward ribose or amino acids. Confinement effectively turns the quantum dice rolls into a structured game, stacking the deck toward higher-order molecules. The most mind-bending implication: this process might still be happening. Europa's subsurface ocean, Pluto's icy plains, or even the permafrost of Mars could currently host quantum-fueled chemistry, silently assembling organics in the dark. From the quantum realm's probabilistic fog to the crisp structures of biochemistry, the universe appears to have a backdoor, one where the coldest, quietest places become workshops for life's delicate architecture. Imagine a world before cells, where the first fragile structures of life weren't complex organisms, but simple bubbles floating, merging, and dividing in the warm alkaline waters of ancient hydrothermal vents. These weren't ordinary soap bubbles, they were lipid membranes, made of fatty acids that somehow learned to trap and protect the chemistry bubbling inside them. This is the lipid world hypothesis, a theory suggesting that life's first boundaries weren't biological inventions, but natural formations emerging from the molecular ballet of early Earth's oceans. The magic begins with fatty acids' long carbon chains with a water-loving head and a water-fleeing tail. In the alkaline fluids seeping from hydrothermal vents, these molecules behave like nature's origami masters. When concentrations reach a critical threshold, they spontaneously curl into hollow spheres, their tails huddling together to avoid water while their heads face outward, creating a delicate but stable barrier. Lab experiments at University College London have recreated these conditions, mixing simple fatty acids like olate with alkaline solutions mimicking vent fluids. Within hours, microscopic bubbles form, some persisting for weeks, a striking demonstration of how easily the building blocks of cells could have assembled without any guiding hand. But why alkaline vents? These unique environments offer a perfect storm of conditions. Their mineral-rich fluids provide a steady supply of fatty acid precursors, while the porous chimneys act as natural sieves, concentrating molecules in their twisting channels. Even more crucially, the pH gradient between the vent's alkaline discharge and the acidic ocean creates a subtle but relentless energy source. Modern cells use similar proton gradients to power their metabolism. Could lipid bubbles have tapped into this same primal energy? The evidence keeps mounting. In 2021, researchers at the Earth Life Science Institute observed something extraordinary in their vent simulations. Not only did lipid bubbles form, but under turbulent conditions mimicking ancient seawater currents, they began exhibiting lifelike behaviors. Some grew by absorbing nearby fatty acids, then split when they reached unstable sizes, a crude form of reproduction. Others merged, exchanging contents in a primitive version of genetic sharing. Most remarkably, a few even maintained internal pH differences, hinting at the earliest stirrings of energy harvesting. Critics argue that lipid bubbles lack the complexity to store information like RNA or DNA. Yet recent breakthroughs suggest they didn't need to. Experiments show that certain fatty acid membranes can selectively trap molecules concentrating nucleotides while excluding destructive salts. Other studies reveal that lipid composition affects stability. Mixtures resembling those found in meteorites produce unusually resilient bubbles capable of surviving temperature swings and mechanical stress. It's as if the chemistry itself was optimizing for function long before natural selection took over. What makes this theory so compelling is its simplicity. Unlike elaborate scenarios requiring perfect storms of lightning or comet deliveries, lipid world chemistry unfolds almost inevitably wherever fatty acids meet alkaline water conditions likely widespread on early Earth. From the vents' mineral pores to tide pools scummed with organic films, the planet might have been teeming with these protocells, each a tiny laboratory experimenting with different molecular combinations. Most would have collapsed, their contents dispersing back into the chaos, but a few, by chance or chemistry, might have stumbled upon the right mix to cross the threshold from bubble to being. Deep in the ocean's darkness, where chemistry shades into biology, these flickering membranes could have been the universe's first attempt at containment, a fragile partition between the self and the world that would one day evolve into the complex cells were made of. The echoes of this process might still resonate in every living membrane today, from the outermost layer of your skin to the microscopic boundaries of your neurons. Life didn't invent the container, it inherited it from the patient, persistent experiments of a bubbling, alkaline sea. Cosmic rays, those ultra-high energy particles rocketing through space at nearly the speed of light, might seem like cosmic wrecking balls, smashing apart anything in their path. But in the chaos of their collisions, there's an unexpected twist. These violent intruders could have been master architects, stitching simple molecules into the long chains life depends on. At CERN Nuclear Research Facility in 2021, scientists recreated these primordial particle strikes in a cloud chamber, revealing a startling phenomenon. When they bombarded mixtures of water vapor, carbon dioxide, and ammonia with proton beams mimicking cosmic rays, the energy didn't just break bonds, it forged them, polymerizing the gases into complex organic strands almost like an invisible molecular sewing machine. The secret lies in the way these particles interact with matter. Unlike gentle chemical reactions that need heat or catalysts, cosmic rays deliver concentrated energy bursts along their trajectories, ionizing molecules in their wake. This creates a cascade of secondary particles and free radicals, highly reactive fragments that can link together before they dissipate. CERN experiments showed these radicals preferentially forming stable carbon-nitrogen and carbon-carbon bonds, the same skeletal framework found in proteins and nucleic acids. It's as if the randomness of deep space carried a hidden bias, favoring the very connections biology would later depend on. But here's the real surprise: this process thrives in environments where traditional chemistry fails. The frigid surfaces of interstellar dust grains, the thin atmospheres of icy moons, even the upper layers of Earth's early air, all places too cold or diffuse for normal reactions, become productive workshops under cosmic ray bombardment. Data from the Rosetta mission supports this, revealing complex organics on Comet 67P's surface, exactly where cosmic rays would have struck hardest. The implications are staggering. Life's precursors might not have needed a warm, cozy cradle. They could have been knit together in the bitter cold of space, energized by particles from distant supernova. What makes cosmic ray polymerization so compelling is its universality. While hydrothermal vents or tidal pools are localized, these high-energy particles rain down everywhere, turning entire planets or moons into potential reaction vessels. And the timescales aren't limiting either. Simulations from the University of Tokyo estimate that over a few hundred million years, cosmic rays could have deposited enough organic material to coat early Earth's oceans with a 10-meter-thick layer of polymerized compounds. Yet the theory isn't without its mysteries. How did these random polymers transition into functional, self-replicating systems? Some researchers point to natural selection at the molecular level. Certain chain configurations might have resisted degradation better, accidentally stumbling into protoenzymatic functions. Others speculate that cosmic ray synthesized polymers acted as templates, guiding simpler molecules into ordered arrangements. Whatever the path, one thing's clear: the universe has always been more inventive than we imagined, turning even the most destructive forces into unexpected collaborators in life's origin story. From the particle accelerators of Geneva to the frozen wastes of interstellar space, this idea reshapes our search for life's beginnings. It suggests that the ingredients for biology aren't just lying around, they're being actively assembled, even now, by the silent rain of particles from dying stars. The next time you see a shooting star streak across the night sky, remember, its cousins might have been the unseen weavers of life's first threads. Not all worlds need a blazing sun to cook up life's ingredients. Some might have relied on the silent, relentless kneading of gravity itself. Imagine a moon orbiting a young gas giant, its icy crust stretched and compressed by tidal forces as it swings through its elliptical orbit. This isn't just geological exercise, it's a planetary-scale chemistry set. With each flex of the moon's interior, friction generates heat, melting subsurface ice into vast, salt-laden oceans, and within these dark, pressurized brines, something extraordinary could have been stirring, a slow dance of organic molecules, forged not by sunlight or lightning, but by the rhythmic pulse of gravity's embrace. Saturn's moon Enceladus offers a breathtaking glimpse of this process in action. When NASA Cassini spacecraft first detected towering plumes erupting from its south pole, the discovery sent shockwaves through the scientific community. Here was proof that this tiny, frozen world just 500 kilometers across harbored a subsurface ocean kept liquid by tidal heating. But the real stunner came when Cassini's mass spectrometer analyzed the plume's composition. Mixed with the water vapor were traces of methane, carbon dioxide, ammonia, and even complex organics like formaldehyde and hydrogen cyanide, the very ingredients that, on Earth, are considered precursors to life. How does a moon barely wider than Arizona become an organic factory? The answer lies in its tortured core. As Enceladus orbits Saturn, the gas giant's immense gravity tugs unevenly on the moon's rocky interior, generating friction that can heat localized regions to over 90 degrees Celsius. This heat seeps upward through cracks in the ocean floor, creating hydrothermal systems eerily similar to Earth's black smokers. Lab experiments mimicking these conditions, salty water, high pressure, and mineral-rich surfaces, have shown that such environments can synthesize amino acids and even short peptide chains without any external energy source. The tidal energy does all the work, acting like an invisible stir rod churning the moon's hidden ocean into a primordial broth. But Enceladus isn't unique. Europa, orbiting Jupiter, shows even stronger evidence of tidal heating, with its fractured ice shell and possible plumes hinting at a subsurface ocean twice the volume of Earth's seas. Early in our solar system's history, when gas giants orbited closer to the Sun and their gravitational tides were even fiercer, dozens of moons might have experienced similar conditions. Picture a young Earth, its sky filled not just with the Sun and Moon we know today, but with multiple tidal-heated satellites, each a potential crucible for organic synthesis, each spraying plumes of life's precursors into space. Some models suggest these molecules could have rained down on Earth during the late heavy bombardment, delivering a ready-made toolkit for biology. The elegance of tidal heating lies in its persistence. Unlike lightning strikes or meteor impacts, which are fleeting, the flexing of a moon's core is a constant billion-year process. It doesn't just create organics, it nurtures them, providing stable environments where molecules can accumulate, interact, and grow more complex without being scattered or destroyed. Recent simulations from the University of California show that tidal forces could even drive circulation patterns in subsurface oceans, creating localized zones where organics concentrate like swirling eddies in a cosmic teacup. Yet mysteries remain. How do delicate organics survive the journey from deep-sea vents to erupting plumes? Cassini's data hints at an answer. The plume's ice grains act as protective shells, encasing fragile molecules in a frozen embrace as they jet into space. And if Enceladus can preserve its chemistry this way, why not other moons? From the geysers of Triton to the hidden oceans of Ganymede, tidal heating might be the universe's most widespread and overlooked recipe for organic synthesis. What started as a curious feature of orbital mechanics now looks like a galactic-scale alchemy. In the darkness between stars, where no sunlight reaches, the silent tug of gravity might be the unseen hand stirring the pot of life's beginnings. From the plumes of Enceladus to the hypothetical oceans of exomoons circling distant gas giants, the ingredients for biology could be simmering everywhere, not despite the cold and dark, but because of it. Slime molds, those brainless, amoeba-like organisms creeping across forest floors, might seem like unlikely teachers in the story of life's origins, yet their peculiar talent following chemical trails to congregate in nutrient-rich areas could rewrite our understanding of how lifeless molecules first organize themselves into something greater. This behavior, known as chemotaxis, isn't just biological. It's a fundamental physical principle that might have guided prebiotic chemistry long before cells existed. Imagine a primordial pond where simple organic compounds, instead of drifting aimlessly, actively migrated toward zones of higher concentration, drawn by gradients as subtle as the whisper of a scent on the wind. Recent experiments with synthetic microdroplets have brought this eerie possibility to life. Scientists at the University of Strasbourg designed oil-in-water droplets containing weak acids, stand-ins for early organic molecules. When they introduced a pH gradient to the system, something remarkable unfolded. The droplets didn't just diffuse passively, they moved, creeping along the gradient like microscopic explorers drawn to an invisible beacon. The mechanism, as the droplets encountered regions of differing acidity, asymmetrical reactions at their surfaces generated tiny propulsion forces. It's as if the chemistry itself became a navigation system, steering prebiotic building blocks toward one another with uncanny precision. But the real revelation came when researchers added mineral particles to the mix. Certain clays and sulfides, common on early Earth, acted like chemical signposts, altering local gradients in ways that created convergence points. Droplets gathered around these mineral hubs, their concentrations skyrocketing from dilute to dense within hours. This mirrors how modern slime molds follow trails of cyclic AMP to aggregate into multicellular structures, except here, the players weren't living organisms, but inanimate blobs obeying the quiet logic of physical chemistry. What makes this theory so compelling is its universality. Chemical gradients aren't rare, they're inevitable wherever energy flows through a system. A hydrothermal vent spewing hot, alkaline fluid into cold seawater creates gradients. A tidal pool evaporating under the sun forms salt and pH gradients. Even sunlight striking a pond's surface can set up temperature and oxidation gradients that molecules might have exploited. The universe, it seems, is riddled with invisible breadcrumb trails, each one a potential pathway from chaos to order. Critics argue that chemotaxis alone doesn't explain life's leap to complexity. Yet when combined with other prebiotic processes like polymerization at mineral surfaces or encapsulation in lipid membranes, it solves a critical bottleneck, the concentration problem. Life's chemistry requires molecules to meet at high densities, but early Earth's oceans were overwhelmingly dilute. Chemotaxis offers an elegant solution, showing how randomness could give way to directed motion, transforming a sparse soup into a rich broth ripe for reaction. From the pulsating colonies of slime molds to the self-organizing droplets in labs, This idea blurs the line between physics and biology. It suggests that the urge to gather, to seek, to coalesce behaviors we associate with life might be written into the fabric of chemistry itself, waiting only for the right conditions to awaken. The next time you see rainwater bead up on a leaf, remember, those droplets might be obeying the same ancient imperatives that once set the stage for life's grand debut. What if the secret to life's origins isn't a single eureka moment, but a symphony of processes working in concert? After exploring 29 distinct theories, from tidal pools to cosmic rays, we're left with a tantalizing possibility: the truth might lie in their convergence. Cutting-edge computational models now suggest that life's building blocks didn't emerge from one perfect environment, but from a dynamic interplay of multiple mechanisms, each filling gaps the others couldn't. Imagine a primordial Earth where hydrothermal vents provided energy and minerals, while tidal pools concentrated organics, and meteorite impacts delivered critical phosphorus, all while atmospheric haze shielded delicate molecules from UV radiation. This isn't just speculation, it's what happens when scientists simulate early Earth with all these factors running simultaneously. One groundbreaking study from the Earth Life Science Institute in Tokyo programmed a virtual early Earth incorporating 5 key theories: volcanic gas chemistry, hydrothermal vent assembly, meteorite delivery, UV-driven atmospheric reactions, and freeze-thaw cycles. The results stunned researchers. While each process achieved limited results alone, their combined effects created a runaway feedback loop. Hydrothermal vents produce simple organics, which were then concentrated by tidal evaporation. These enriched pools were periodically seeded by meteoritic phosphorus, while atmospheric haze particles rained down nitrogen-rich compounds. The model showed molecules advancing toward complexity 10 times faster than any single theory scenario predicted. It's as if Earth's diverse environments were pieces of a locked safe, and only their simultaneous turning could crack the code, but the real magic emerges at the intersections. Take the meeting of deep-sea vents and cosmic dust. Vents excel at creating amino acids, but struggle with nucleotide assembly precisely where interstellar chemistry shines. Models show that cosmic dust particles landing in vent fluids could act as scaffolds, organizing nucleotides into chains while vent heat provides energy. Similarly, lipid membranes forming in tidal pools might have gained stability by incorporating sulfur minerals from nearby volcanic plumes. Even the timing plays a role. Asteroid impacts could have periodically disrupted stagnant systems, resetting conditions to prevent dead ends. Critics argue that hybrid models trade simplicity for complexity, but nature rarely chooses tidy solutions over effective ones. Consider Europa's ocean. We already see tidal heating, hydrothermal activity, and surface chemistry working in tandem. If life's ingredients can collaborate on an ice moon, why not early Earth? The takeaway isn't chaos, but a beautifully orchestrated chaos where each process, however modest, nudge molecules closer to the threshold of life. From quantum tunneling in icy comets to the electric hum of atmospheric plasma, the universe seems to have thrown everything at the wall until something stuck. And perhaps that's the most profound lesson: life's origins weren't a single stroke of luck, but a constellation of chances woven together across a planet-sized laboratory. From the fiery chaos of volcanic vents to the silent dance of cosmic rays across frozen interstellar grains, the story of life's first molecules isn't just one theory, it's a symphony of possibilities. We've journeyed through 30 wildly different explanations, each with its own compelling evidence, from the radioactive beaches that might have jump-started chemistry to the quantum tunneling in deep space that defies classical physics. What's striking isn't just the diversity of ideas, but how many of them might be true simultaneously. Life's ingredients could have been forged in stellar furnaces, assembled on mineral scaffolds, concentrated in tidal pools, and delivered by comets, all before Earth even cooled. Right now, missions like NASA Ocean Worlds program are pushing these theories into uncharted territory. The Cassini spacecraft's discovery of organic plumes on Enceladus and the upcoming Europa Clipper mission, set to launch in 2024, could revolutionize our understanding of where and how life's building blocks form. Imagine if we find not just amino acids on these icy moons, but patterns of molecules that mirror Earth's earliest chemistry. Would that mean life's recipe is universal, written into the fabric of the cosmos itself? But here's where you come in. After 30 theories, which one feels most convincing? Was it the simplicity of the primordial soup, where lightning sparked life in a bottle, the elegance of hydrothermal vents, with their mineral-rich pores acting like tiny laboratories? Or the cosmic audacity of Panspermia, with asteroids ferrying life seeds across the galaxy? Drop your vote in the comments, we're genuinely curious. And this isn't the end of the journey. The more we learn, the deeper the mystery becomes. Upcoming videos will dive into the next big questions. How did these molecules leap from chemistry to biology? What role did Earth's early seasons or magnetic reversals play? And could life's origins be weirder than we've ever imagined, or perhaps even stranger than fiction? Stick around, because the universe has a way of surprising us when we least expect it. Until then, keep looking up and down and back in time, because the story of how we got here is still being written, one groundbreaking discovery